Hi, today we are going to talk about one-dimensional motion. So this is the first lecture of 5 lectures, and all these 5 lectures should cover almost everything about one-dimensional motion at a very simple level. So motion is defined as the consequence of any change in position. So this is a very simple definition, and we can see an example from everyday life saying that if you go from point A to point B, then you're changing your position from A to position B. That is a very simple form of motion that you're causing when you're moving from A to B. Now, motion is described in terms of physical variables, which helps us to understand a deeper notion of motion and understand each motion at a more mathematical level. So these physical quantities are called kinematic variables. These kinematic variables characterizes any motion, okay? And examples of kinematic variables include time, position, distance, displacement, velocity, speed, and so on and so forth. There are many examples. What you would notice that I have underlined some variables with green and other variables with red. So does that make a difference? Yes, it does. It helps us to distinguish between two different physical quantities, or two types of physical quantities that you will encounter in physics. One is scalars, underlined in green, and two is vectors, underlined in red. So how can we define scalars? How are they different from vectors? Well, scalars are any quantities or any variable that can completely be described as by their size or magnitude only. Okay, they don't need you to specify any direction. So example of scalars is speed, distance, etc. So scalar quantities properties would be, they will always be positive because they are just denoting numbers, positive numbers. So a more detailed example of speed would be to say you're driving at a speed of 5 miles an hour, which is too slow, but it is what it is. You are not specifying in which direction you're moving. When we move on to vectors, vector quantities are described by both a size and a direction. So both a magnitude and the direction is required to completely describe a vector. Examples would include velocity, displacement, etc. So how is velocity different from speed? We may know that they describe similar quantities in motion, in that speed is what we call the size or magnitude of velocity. But velocity is different in that when you're driving at 5 miles an hour and you say I'm driving 5 miles an hour due east, when you include that due east, you're saying that this is my velocity because you're also including a direction in which you're moving. Similar to displacement. So how is displacement different from distance? This distance, you can say I have walked from home 5 meters and I've gone back home another 5 meters. So your total distance is 10 meters, right? But in displacement, it's a vector. So it includes, or direction is important for a vector. So when you say you have walked 5 meters from home and then back home another 5 meters, your displacement is actually 0 meters because you have gone in the forward direction of 5 and then in the backward direction 5, and when they sum to 0. Okay, so now let's investigate vectors by looking at a problem. That's what we do in physics. We learn something and we apply it. What does the problem say? It says Isaac Newton, hikes 1.5 miles at an angle of 30 degrees north of east. Then stops for a bit and continues his hike going 2 miles due west from where he stopped from there to reach the famed apple tree of gravity, where he discovered gravity. how far was Newton from his starting position? And fun fact, everything is happening during the Spanish flu pandemic. So let's learn physics when he discovered gravity in a similar kind of situation. All right. Now, what is the first thing we do when solving physics problems? We try to visualize it by drawing a diagram. Okay, and often that diagram, without a diagram, we can't even approach the problem. This is that sort of problem. We can't approach the problem without drawing a diagram. Start with a choice of axis, okay, because here we have north, east, west directions. So without defining which direction is north or which direction is south or east or west, we can't start the problem. All right, so let's draw an axis. So let's say this direction is north and positive. This direction is east and positive. So this is positive x, we can say. This is positive y. So if you're going down, then you're moving in the negative direction or southern direction. If you're going left along the horizontal axis, then you're moving in the negative x, this is a negative y, negative x or westward direction. Okay, so this is how we start off with by defining directions when we use vectors. Okay, so this is up to you. You could have easily set north to be along this or east to be along that. It would be up to you. You could have set this direction to be positive and that direction would be negative. This is completely up to you. Okay, I choose this direction. All right, now let's draw out what's happening. Newton is hiking 1.5 miles at an angle of 30 degrees north of east. So this is north, this is east. So let's say this is around 30 degrees north of east, so in this direction. Okay, so we need a line that is denoting a distance of 1.5 miles. Okay, what do we call that line? Let's say we call this point A. All right, then what? Then he stops at A for a bit, right? He stops for a bit and continues his hike, going 2 miles due west from there. So from A he moves 2 miles due west. So west is in this direction, so in the negative x direction or leftward direction. So from A he moves a total distance of 2 miles in the westward direction. So let's call this B and draw a straight line. Forgive my ineptness in drawing straight lines on the board. Sorry about that. Okay, so this is denoting a distance of 2 miles due west. Oh, I forgot to show the direction on the green line. All right, then what do we want? So this is his journey. So here we have the apple tree. This is our target. So we want to know how far he was from where he started. He started here. So we want to know what is the distance from the apple tree to O. All right, actually we want the displacement, sorry, because we want all these to be vectors. So again, forgive my straight line. It's a very bad straight line, but it will do. Let's say this is Z. Okay, and for some reason I chose to call this point C, which I will keep. All right, now this is the diagram we have, and we can go ahead with solving the problem. So probably you are smarter than me, and you say that, hey, there are multiple ways to solve this problem. First, we don't even need any physics. I've learned cosine rules in trigonometry, and I can use that and find this side pretty easily using that formula. But I always get mixed up using cosines and sine rules. So what I do is I break this down into triangles, and for me that's easier. I don't know about you, but both ways are correct. So let's divide our journey. So let's consider the first part of the journey. Okay, so how do we break that down into triangles? So we can see that this is a triangle, right angle triangle. What is that triangle? We have a point X here, and we have the starting point here, and here we have A, correct? So this line represents 1.5 miles, and also we have the angle here, and we know that this is a right angle. So how does that help? It helps to use basic trigonometry to find this distance. Let's call this y1, and this distance, let's call this x1. So it's very so why are we finding these? We'll shortly find out. So let's see x1. How do we find x1? X1 is just using cosine of 30 is equal to adjacent, which is x1, over hypotenuse, which is 1.5 miles. So x is 1.5 times cosine of 30 miles. Okay, how do we find y1? Well, y1 is found by using sine of 30 equals y1 opposite over hypotenuse, which is again 1.5 miles. So y1 is 1.5 times sine of 30 degrees. So we have x1 and y1. Okay, now let's make some space, and remember we are looking to find this z. What is the next part? So we have broken down the first part of the journey. What about the second part? Well, the second part is simpler than the first part. In that second part, only moved in one specific direction, due west, right? So we don't have to do much about it. Second part is only moving due west. We can say second part pretty simply is just the length of AC, which we can say denote x2 for consistency with x1 as 2 miles, and y2 is the vertical distance or vertical length of the second part of the journey is 0 miles because it didn't move in the vertical direction. Okay, all right, now let's think about the third part of the journey. What do we want? We want to find the length of OC denoted by Z. All right, so let's see what we have in total in independent north, east, west and southward directions. So before moving on, I would like to note that when we work with vectors, x and y are independent variables. So any x quantity will always be compared to other x quantities. So any horizontal vectors can be added or subtracted from other horizontal vectors. any vertical vectors can only be added and subtracted with other vertical vectors. So when you have an angular vector, your first job would be to separate out into its x parts and y parts. So these x and y parts are termed components of a vector, which we will meet shortly in further ahead in the course. Let's carry on. So our goal is to note how much total movement in each x and y direction separately we have had. So total x is equal to x1, which is in this direction, so this is a positive direction. X1, so remember we're dealing with vectors, so x1 is nothing but positive 1.5 cosine 30 miles is implicit, and also x2 is 2 miles. Okay, so 2 miles, but in what direction? It's moving westward, so that's a negative direction. 2 miles. All right, now total means you have to add the 2, so vector x1 plus vector x2 will be 1.5 cosine 30 minus 2. Make sense? All right, so minus, because plus times a minus is a minus. Now let's move on to y. What movements do we have in the y direction? So in the y we have y1, which is again in this upward direction, so this is also positive 1.5 sine 30 miles, and y2 is, with say 0, because there was no movement in the second part of the journey in the vertical direction. So therefore total of y is equal to y1 vector plus y2 vector, which is just 1.5 sine 30. So let's actually calculate the numbers, what we have here. So total x, when you add, gives me negative 0.7. So negative means west. Total y is just positive, which is 0.75 miles. So this positive means it's in the positive direction. Y is positive, x is negative. So this direction was positive y and this is positive x. So if this is 0, then this side is negative x, right? So we have the final triangle. And this last line is what we are looking for, z. Okay, so this is minus 0.7, this is plus 0.75. we want to find what z is. So that is very simple, because this is a right angle triangle and we can basically use Pythagoras theorem. So z square, so let's see that this is giving you just the magnitude. The Pythagoras theorem gives you the magnitude of the vector. So any vector can be solved like this. The magnitude of the vector is the Pythagoras theorem applied to a triangle like this, okay, with its x part and y part as the other sides of the triangle. So we have minus 0.7 squared plus 0.75 squared, and you end up with, so you square root both sides, and actually this is what it is, and z is equal to, let's see what I have found, it is 1.03 miles. So first part is over. You have found the distance from the starting point to the finishing point. Okay? Now, again, we are working with vectors. So we need the direction. So the direction, most simply, can be found by finding the angle between this final vector, z, and the horizontal, or the westward x directional vector. So this is, again, using trigonometry. We have tan theta is equal opposite, that is 0.75, over adjacent, 0.7. Also, never include the negative sign when finding angles. So theta is equal to tan inverse of 0.75 over 0.7. We get theta to be, let's see, drum roll, 47 degrees, and 47 degrees is north of west. So you were going west, and this is the angle you found. So you're going north from the westward direction. So northwest. Hopefully that made sense.